All right. So, as some of you are aware, we are beginning our final, let's say, our final chapter upon completing this year of general chemistry. With everything that we've been working up until this point has been in organic chemistry or general. And when you're talking about general chemistry, that just means you're dealing with substances like you're taking calcium and you're doing some specific reactions, maybe with some hydrochloric acid, okay? And one of the before that of the heat and temperature chapter that we had done, chapter 12, in other words, leading up to last week, everything had probably dealt with all these types of elements and molecules and compounds, which we know becomes CaCl2 plus H2. Okay, so how the year had started would be okay if you had 300 grams of calcium, how many moles is that? Okay, or if you had 0.41 mole of calcium, how many grams would that be? That's how the year started. Then from there, we started talking about electrons and chemical bonds and empirical and molecular formulas. Then we ended the semester with chemical reactions. And one of the things we try to imprint in your mind as freshmen is that you cannot do general chemistry without balancing chemical reactions. So then when we came back in January, we started talking about stoichiometry, which ended up saying, okay, if you had those same 300 grams, okay, how many maybe grams of X amount of grams of calcium chloride could you make? Then probably the most difficult portion of this semester, which maybe with the exception of this, would be if you took those same 300 grams and said how many liters of hydrogen gas would be given off. So a lot of these concepts have led up to that point, the gas stoichiometry, and then as you're aware, last chapter was mass, specific heat, change in temperature, and then mass times heat of fusion or heat of vaporization. That was last chapter. Now everything leading up to this point is just mainly hydrocarbons, hydrogen and carbon. Okay, and that maybe sounds familiar from when you were freshmen. You learned the first type of combustion reactions. Okay, probably a lot of you are experiencing this just like ourselves. You walk out to your deck. We don't do any more of these chemical reactions, but this is really what you're doing. You're taking this substance, and then with oxygen in the air, of course, you're producing these byproducts, and then some water as well. This was still maybe some general chemistry, but it's got organic chemistry roots in mind because, again, we're just dealing with hydrocarbons only, compounds with hydrogen and carbon. Hence, we call them hydrocarbons. Okay, so some of this might look familiar from 2 and 3 years ago. Okay, we start with just naming and writing out formulas for the first 10 organic compounds. Okay, and that would be starting with the simplest. Okay. And I want you to see if you can recognize a pattern that arises from this. Okay? While I continue doing some of my weightlifting here at the same time, we got to make sure we're fueled up. Got the right cup here, right? Now, don't focus on this. Look at that. Don't see what I'm doing. Okay, so that pattern that arises is each compound is increasing by a number of 1, and the number of hydrogens is increasing by a number of 2. Okay, So then what we see here, now when you were a freshman, we had, as you're aware, lecture notes that would accompany this to help us explain this. We go quite a bit faster, as you would probably agree, as juniors and seniors in the general chemistry. And then for those of you who maybe decide, you know, I think that I'm going to have organic and biochemistry in the future, then we go at even a quicker rate. So with this, these types of formulas, or what we call molecular formulas, okay, it's just showing you what molecules or elements are within each one of these compounds. And then these are what we call structural formulas, because it shows you the same number of elements that's in the molecular formula, but then just shows you the different structure. So as organic chemists, to save time, if you're only dealing with hydrocarbons like this, you don't need to keep writing hydrogen every time, because it just seems rather repetitive. So basing that off of prior knowledge, if you had to write the formula for sodium chloride or hydrochloric acid or sulfuric acid, so NaCl, or, and I think I said hydrochloric acid or sulfuric acid. Okay. Reason I like to put multiple examples up here is, notice we don't write this as Na1Cl1, H1, or Cl1. It's just understood that once you write the element down, that you have one of those atoms present. Okay? It's when you see something other than one, you have to change that to whatever is available or what's ever present in that formula. Notice we don't write H1S1O4, because to complete this compound out, you have to have two atoms of hydrogen and 4 atoms of oxygen surrounding that central sulfur atom. So to finish our point, you don't write H2S1O4. It's just understood that you have 1 atom of sulfur. So the same type of logic would apply to this, with the idea that it's just understood that if all you have present is hydrogen atoms, you don't need to write it like this. And this is called your structural formula. These are your structural formulas. So it just shows you the number of atoms that are present and what the structure actually looks like. Now, you might be telling yourself, well, that's pretty straightforward, and I would tend to agree. It's once you get to some of these larger hydrocarbons that the structural formula becomes more important. Because one of the concepts that I think is difficult for any student for when they encounter it for the first time, or for the first time when it's a review, is dealing with that of isomers. And we'll get to that at a later time. Okay, so what do we have so far? These are all alkanes increasing by number 1, these increasing by number of 2. And the reason that we see that is there was a formula that you probably learned as freshmen. It was 2n plus 2. Okay, so what that means then, if you're putting the number of carbons in as 2, okay, so you just put 2 in for n, you put 2n in for this variable 2, so 2 times 2 is 4, 2 more hydrogens on the end, that's where you get the number 6, okay, so C2, 2 times 2 is 4, plus 2 more gives you 6. You could do the same thing here. These are where these numbers are coming from. You put 3 in for n, then you put n in here, 3 times 2 is 6, plus 2 more gives you 8. That's where these numbers are, again, coming from. Okay, so as we proceed, we'll go ahead and write more of these structural formulas. if you possibly remember, one carbon length, this is natural gas or methane. Then we move on to ethane. And then should you be out on your deck or patio or whatever running your grill, inside that tank you have propane. And then if you have a liquid lighter, for the physical properties of these hydrocarbons are always changing. Propane is rather unique because it's stored as a liquid, and that's when it's rolling down the road. You see these big trucks that have a white tank on the back. Since it's pressurized, it's in its liquid state, but once you release that pressure, it's going to come out as a gas instead of a liquid, so that's why it makes it really easy to transport propane. Then the physical properties change again. Once you get past number 3, go on to number 4, which is butane. This is a liquid now. It's all liquid, so just like any other, I want to say, grill lighter, because a lot of people would refer to cigarette lighters too. And should any of you be doing that, whether it's Mr. Paulson or myself, we'd like to take our whatever our shoe size is and boot you on the backside and say, don't do that. Okay. But regardless, those types of substances are butane lighters. Whether it's on the grill, it's always going to be a liquid. Butane lighters. Once you get past number 4, then you start naming the geometrical shapes. Okay. So, what is a 5-sided figure called? Well, of course, it's a pentagon. Okay. Where the Department of Defense is, you would say, is in a building called the Pentagon. It's got 4 sides, which decided to put an extra one on there. Okay. So C5, H, how many? Well, if you use that formula, 2n plus 2, 2 times 5 is 10, plus 2 more means you're going to have 12, and it should be 2 more than what we see here, and that is the case. Okay, so this is pentane. Then a 6-sided figure is a hexagon, so you would have hexane. And then some authors like to say septane. I prefer you use heptane instead. That's a 7-sided figure. Then an 8-sided figure is an octagon. Okay, octane, nonane, and then 10 years in a decade, so we call this decane then. And you could fill these in if you would so choose. C6, H14, C7, H16, octane, C8, H18, and so on and so forth. Okay, in other words, C9, H20, C10, H22. So I'll go ahead and give you a little bit of time to get caught up with that. So I'm just going to hit pause. I guess perhaps hitting pause doesn't help on this end. You'd have to hit pause on your end. Okay. So I think we can go ahead and erase this. And again, one of the things that we try to ingrain into your mind is the idea that when you learn this as freshmen, again, you have lecture materials to accompany that. We don't have that here because we go at such a faster pace. And then again, for the organic class, we go as a faster pace even then, because there's just more material that you have to, I wouldn't say shrink into a short amount of a time frame, but just the idea that with everything that you learned with that of general chemistry before this, and I think you've heard me make reference before, is the idea that that's probably about maybe a month, maybe just a little over a month in college chemistry is what we cover in about 7.5 months, just because that time frame, you just go at such a faster pace. Okay, so the next thing we want to talk about, okay, is that of isomers, okay? And isomers do not begin until you hit your fourth carbon, okay? And this is why. And here again, like I told the freshmen before, and I'll say it here, we'll catch some of you sleeping again with the idea, here's the concept we're talking about. If you were to see this, chromium 3 nitrate, okay? I tell the freshmen, I still see juniors and sometimes even seniors doing this. They're going to look at this and say, oh, chromium, well, that's Cr, that's fine. Nitrate, that's NO3. Well, what's this funny thing? Oh, that must be down there. Don't do that. This is not telling you you have 3 chromium atoms. It's telling you that it's got a +3 charge, okay? That's an easy trap to fall into. So the point we're trying to make here is when these isomers start, okay? Because when we look at this, we know that this is propane, okay? If you remember what an isomer is, it's the same molecular formula, but that of a different structure. So what we see is these are 2 different structures. This is a straight chain of propane. This must be a branched chain, okay? And that's the trap that some students perhaps fall into, and that's why we did that chromium 3 nitrate example. That Roman numeral is not telling you the number of atoms, it's telling you the charge. Because when we look at this, we've established this is propane, but so is this. Okay, it's just bent. It's just going in a bent chain like this, because when we name these organic compounds, you have to find the longest continuous chain first, and then perhaps anything that's branching off of that parent chain. So we'll erase this, okay, and then we're just going to go ahead and attach another carbon on there. All right, so one of the aspects that may jar your memory is something like this and this, and that was last year, or excuse me, 2 and 3 years ago. This is a methyl group. This is an ethyl group. Those are what you learned as freshmen. This year as juniors, okay, and seniors, you're going to learn C3H7. That is a propyl group. And then, we'll say X marks the spot. This is called an isopropyl group. Okay? And notice that these formulas are the exact same. C3H7, 1, 2, 3. There's your 3 carbons. 3 hydrogens. 3 hydrogens is 6. 1 more gives you 7. These are isomers of one another, even as derivatives. Okay? And the reason that we need to get up to that isopropyl group is that those of you who go on to take this course next year, you have 4 more derivatives, and that would be your butyl groups, which is just straight up butyl. It's secondary butyl, isobutyl, and tertiary butyl groups. Okay, so we try to go at a pace and add a little more content as we continually go forward. Now, that doesn't state how we have arrived at this. And it was earlier today that this is the example that we like to use. Going back to general chemistry, okay? If you are looking on the periodic table for that element, you look and see, well, it's got an I in there. Oh, well, that must be iron, okay? I would make sense. I would agree, but we know that that's not iron, that's iodine, okay? Well, it's got an I and an R in it. That must be iron. Of course, that's not the case either. That is iridium. And then might see an I and an N somewhere. It's got an I and an N. Of course, that's not the case either. That's indolium. Then finally, when you look at box number 26, okay? Once you look at element box 26, you see these two letters, okay? That is iron, because different types of metals that you look are referred to as ferrous metals. If that's the case, that means it has iron in it. So why is that relevant? Because when we look at why this is named as it is, that is translated in Latin to English for iron. So that's why you see Fe as iron. It's derived from the Latin name. In other words, that's where it comes from. Okay? So what we see here, we know that this is methane. A derivation of methane is what we call a methyl group. This is derived from the alkane. That's where it comes from. An ethyl group is derived from the alkane. Ethane, one less hydrogen, gives you an ethyl group. Okay? Then that would continually go on and so forth as we go further along. This, a propyl group, is derived from propane. And then notice we don't do any butyl groups here. We save that for senior level chemistry with the organic and biochemistry class. Okay, so these again are your derivatives. They're derived from their alkane counterparts. Okay, so just to give us a little space, go ahead and erase all of this. Remember we talked about isomers. Okay, find your longest continuous chain. Well, it's 4, it's straight, so we know that is butane. But one of the things that can happen, boy, I had to switch laptops, and I think the camera resolution is a little better on this one than the one I was using last night and earlier today. But we see the formula C4H10, but if we take this carbon off of there and put it, well, we'll just put them up here, because I think we can see that that's a different color. This also still has a formula of C4H10, just like butane. 1, 2, 3, 4. There's your 4 carbons. We've got 3. We've got 6. We've got 9 hydrogens. One more in the bottom would give you 10, just like that of butane. But the structure is totally different. And in many different authors, they will call this isobutane, which to me, I prefer we do not use this. We use a numbering system. So in this case, well, I see we're up to 23 minutes. We'll try to wrap this up within the next 5 or so. There's nothing wrong with putting little numbers in here. Okay, that tells you that your parent chain is 3 carbons long. Is there anything branching off of there? Well, yes, there is. There is this CH3 compound. Remember, we called a methyl group. So the first thing you're going to want to do is name your parent chain, PROP, 3 carbons in length. Is there anything branching off of there? Of course, yes, there is. There's a molecule with a formula of CH3. So that CH3 means there's a methyl group branching off of this alkane. Okay. So on our second carbon, we have a methyl group. So this is 2-methylpropane, which is an isomer of butane. Because remember, this has a formula of C4H10. So does butane, C4H10. Same molecular formulas, but the structure is different. The reason that's important is because the physical properties It's mainly its melting point is going to be different. We don't spend a whole lot of time on that in senior level chemistry until we get to biochemical compounds we call lipids, okay? Because a lot of things that would apply to that and what would possibly make sense is that lipids have different types of melting points, and butter or margarine is a type of lipid. For anyone who's left milk sit out overnight, okay, like a carton of milk or a glass of milk, or left your butter left out overnight, what happens is a lot of those unsaturated fatty acids start to break down, and that's why that starts to smell, because the physical properties of them have melting points that are so low. That's why they have to be kept in the fridge so they do not decompose. This is the same concept, but at a lot smaller, structure, but a lot smaller scale. Okay. Some of you may have noticed some of the lipids that we've had up on the board that I've left up there for visual references for the seniors. Okay, so should at any time you be having problems with these, okay, yes, you can come in and talk to myself, but chances are pretty good if you approach one of the 9 seniors that are in this classroom every day from 8:30 to 9:20, if you just say, could you please help me with this, chances are pretty good they will probably help you with it, because we are going at a faster rate than what you learned this as freshmen. Okay, so I see we're up to 26 minutes. So let's go ahead and put something a little more complex. Okay, let's go ahead and go with so we got C8, H18, we know as octane. I think I put octane, 2, 4, 6, 8. Yep, that's octane, C8, H18. Okay, so where this is coming from, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's go ahead and put some isomers up there. We can do this. Okay, and you might be telling yourself, wait a minute, there's only 6 carbons in that parent chain. I would agree. Okay, let's go ahead and keep it a little more simple. Let's go ahead and make it 7. Okay, so I'll go ahead and put this down here. And again, notice that what we had done is we had numbered our carbons from left to right. Okay, and an example to think of is, we're not that far yet with the freshmen, is think of golf. I guess today is the first day of the Masters tournament, which they would have teed off by now down in Georgia. Okay, and think of golf. What is the concept of golf? Get that funny little ball from the tee box into that funny little hole on the green in the least number of strokes. Okay, so in this case, not only do these carbons, they don't always go from left to right. They can go right to left, if you remember that from 2 and 3 years ago. So to make sense of that, if we go left to right, 1, 2, 3, 4, 5, 6, 7, or if we go right to left, 1, 2, 3, 4, 5, 6, 7, okay, what gives you the lower combination? If we go left to right, this methyl group is on number 5. If we go right to left, well then that methyl group is on number 3. So that means we have to go right to left. We can eliminate these. Then the next thing you'd want to do, name your parent chain. Well, here it is. It's 7. So therefore, we know that is, I'm running out of space here. Well, I think it's a different color. You'll be able to see that. Heptane. Okay. Here's our parent chain, 7 carbons in length. Is there anything branching off of that? And yes, there is. There's a methyl group that's located on our 3rd carbon. So we have to account for that. So one of the things you can always do is reverse engineer this and go backwards. Okay. And that would be as follows. Okay. This is telling you your organic family. It's an alkane. This is telling you your parent chain, that there's 7 of them. There they are. This is saying there's a methyl group. And remember, a methyl group has a formula of CH3. There's a CH3 group. And then this is telling you where it's at on the 3rd carbon. Okay? So notice if we add all these together, okay, we know we've got 7 carbons. There's number 8. How many hydrogens do we have? Well, there's 3, 5, 7, 9, 10, because this is a carbon to carbon bond, not carbon to hydrogen. 10, 12, 15, and 3 more gives you 18. Okay, here's octane that has C8H18. This also has C8H18, but notice the structure is different. That's what we mean by talking about an isomer. Okay, these are isomers of one another, which there are actually quite a few. I just want to put one more up on the board because I see we're up to 32 minutes, and I think that's getting to about the time we need to wrap things up here for the weekend. Okay, so let's go ahead and chop 2 of these off. Okay, and let's just start with a new example altogether. I think that would be better. Okay. So find your longest continuous chain first. Okay. Do we go 1, 2, 3, 4, 5? Well, we could, but you still have more carbons over here. Is it 1, 2, 3, 4, 5, 6, 7? Okay. There's a longer continuous chain. Or could we go 1, 2, 3, 4, 5, 6, 7? So you either go straight this direction, or up and over, or over this direction, or over and down. Okay, well, let's see once what happens. If we go right to left, like we did in our prior example, 1, 2, 3, 4, 5, 6, 7, okay, or are we going to go left to right? 1, 2, 3, 4, 5, 6, and 7. Okay. One thing that we do know for certain is that we've got a 7-carbon alkane compound. So the prefix for that is HEPT, 7 carbons. Okay. It's an alkane. Okay. So then, is there anything branching off of those 7 carbons? Yes, there is. Okay, and whether you choose to do it like this, or if you like putting these little numbers in here, that's fine as well. So what would give us our smaller combination? If we go left to right, we've got 2 and we've got 4. Okay, if we go right to left, we've got 4 and we've got 6. So which one gives you the smaller combination? Of course, going in that direction. So we've got an alkane that's 7 carbons in length, and it's got 2 derivatives on this branched chain. Okay, and where are those located? Well, there's one on the 2nd and there's one on the 4th, so we can eliminate this. Okay, we can eliminate this. This is where it gets to be perhaps a little tricky, is on the 2nd and 4th, we have to account for them. So 2, 4, and we know that those are methyl groups, but the aspect that happens, if you possibly remember from 2 and 3 years ago, we don't just say 2, 4 methyl heptane. You have to account for having 2 derivatives on there, and you'd put di on there. And the reason that we want to get to something like this is because these have to be, these don't count for alphabetizing. This does. That starts when we have multiple derivatives on there with different letters like ethyl groups and propyl groups, but we'll get to that at a later time. Because we want to try to take this in a progressive manner, because one of the things that happens is eventually, okay, we're not always going to be talking about alkanes. We might be dealing with something like this. Okay. Now you've changed your organic family. We've got a double bond in there. That would be 2-heptene. Okay. So this is one of the things we'll be working on next week. This is an alkene because there's a double bond in there. Okay. And then also we'll be doing ring structures as well. But I see we're up to 37 minutes. That's probably enough for now. So enjoy your Easter break, and we will catch up to you on Tuesday. And I know some of you are going to be gone for track, so I can't stress this enough. It is your responsibility to try to stay as current as you can with this content with the Science Channel. It's the best way that we can convey that information to you. Again, happy Easter, and we will catch up to you next time. And probably a lot of you will hear, he's risen. So yes, he's risen indeed, and experience that joy with your family on Sunday. Catch up to you next Tuesday and Wednesday.